Welcome back to the Deep Dive, the place where we take the essential blueprints of a complex topic and hand you the synthesized, actionable knowledge.
And today, we are really getting into the foundations, the absolute bedrock.
We really are. We're decoding the geographical organization of the cloud itself,
Yeah.
specifically looking at Google Cloud Platform's global infrastructure, its map of regions, zones, and that powerful layer of global services that sits on top of everything.
Right, and this isn't just about, reading a map. It's about understanding the core engineering choices that enable modern computing resilience.
Mm.
Every single decision you make about where to place your data region or zone, it has these cascading effects on performance, on cost, and crucially, on legal compliance.
Absolutely. So our mission today is to cut through the jargon, really, and give you the shortcut to making those informed architectural decisions. We're drilling down into the knowledge that dictates application performance, that locks down data residency compliance, and, well, it forms the bedrock of every successful disaster recovery strategy.
And critically, this knowledge is also the entry point to understanding higher-level security architecture. I mean, when we talk about something like IAM identity and access management...
Those security controls.
Exactly. The rules that govern who can touch your data, those controls are inherently linked to where that resource physically is. So understanding this hierarchy, global region zones, it's the groundwork for figuring out how resource location drives your access policies. It's this concept of global control over local resources.
Oh, I love that framing. Global control over local resources.
Yep.
That is the big picture hook we're pursuing.
Right.
We need to break down these foundational concepts so you can design scalable systems that survive catastrophes, stay compliant, and all while, minimizing latency for your users.
At the end of the day, the difference between success and failure in a global deployment can often come down to knowing exactly where to put your compute engine instance.
It's that simple and that complex.
It is. And to do that, we have to start at the physical level, the actual dirt and concrete. Let's look at the two foundational building blocks that form the basis of the entire GCP architecture.
Okay, let's unpack this with the largest physical unit of scale, the region. We see these standardized codes, like US Central 1.
Which is Iowa for GCP.
Right, Iowa. Or Europe West 1 in Belgium. We know they're geographic areas, but what are the technical characteristics that make a GCP region such a powerful, isolated architectural boundary?
Well, a region is defined as a specific, isolated geographic location where you deploy your resources. You nailed the naming. The codes are basically precise physical addresses. But the real power of the region lies in the level of separation Google has engineered into it.
Tell me more about that separation. If US Central 1 is, a data center campus in Iowa, what stops a massive power outage in Iowa from impacting other regions?
And that gets us to the first, and I would argue the most crucial characteristic, geographic isolation. Regions are explicitly designed to be physically and logically independent.
So they're like islands.
Massive fault domain islands, yes. They are separated by hundreds, sometimes thousands of miles. And that distance protects against these widespread regional events, things like major earthquakes, huge cascading power grid failures.
The really big stuff.
The really big stuff. Even widespread severe weather or, political instability in a specific country.
So this is the strategic decision point for disaster recovery planning. If I'm worried about an actual widespread catastrophe, distance is my friend.
Precisely. If one region fails completely, the other regions scattered across the globe are designed not to even notice, or at least not to suffer any operational impact. And that geographic separation is enforced by the second characteristic, independent infrastructure.
Independent how?
Each region operates with its own completely separate power, cooling, and networking infrastructure.
And we're not just talking about having a few redundant generators on site.
Oh, no, not at all. We're talking about sourcing power from different geographically separated utility substations. The network connections that feed and connect that region are often separate physical fiber optic routes, part of Google's own private global network, that avoid relying on the same terrestrial choke points or exchanges.
That sounds like an immense financial commitment just to ensure that level of separation. And architects should really appreciate that they are essentially buying autonomy from a localized failure when they select a region.
That's the cost of robustness, right? And it's what enables the third characteristic, which is often the primary driver for picking a region in the first place, data residency.
Great. Compliance.
This is where compliance and legality intersect with the physical infrastructure. Regions allow you to mandate with absolute precision where your data is stored and where it's processed.
Let's elaborate on that. When we talk about something like GDPR in Europe or HIPAA for health information in the US, what specifically does choosing the region allow an architect to guarantee?
It lets them guarantee data sovereignty, which is actually a bit more stringent than just residency.
How so?
Residency just means the data is stored there. Sovereignty means the data is stored, and it's subject to the laws of that specific jurisdiction. So if you choose Europe West 1, you're legally assuring your clients and your regulators that their data will never leave the EU boundary. This is often the non-negotiable factor.
So it trumps other concerns.
Completely. An architect might find that Central 1 is cheaper or faster, but if their application processes health records for, say, French citizens, they must default to a European region. Compliance overrules everything else: cost, performance, you name it.
That really puts the brakes on any purely optimization-driven architectural plan. The region is fundamentally a legal boundary, too.
Absolutely. And that brings us to the fourth characteristic, which is intensely focused on the user experience: latency.
Right, the speed of light.
The speed of light is the hard ceiling, you're right. While we might want to pick a region based on cost or some specialized service availability, the physical distance between that region and the majority of your users imposes limits.
So if my users are in Sydney, Australia, and my server is in Iowa,
Every single request and response has to travel thousands of miles of fiber optic cable. That adds measurable lag, even if the connection is optimized on Google's private network.
and that lag is a killer for user experience.
It absolutely is.
Yeah.
Choosing a region close to your users, say, deploying in Australia's Southeast 1 for those Sydney users, directly and significantly improves application performance. It leads to a much snappier experience.
Yeah.
High latency degrades user satisfaction, it increases abandonment rates for e-commerce, and it can make interactive applications totally unusable.
It's a fantastic combination of constraints when you think about it. You have to pick a region that is geographically distant from your primary one for data,
Right.
geographically close to your users for latency, and strictly within a certain legal boundary for residency. It's never a simple choice.
No, it's the first layer of necessary complexity. A region is your geographic, your regulatory, and your disaster containment boundary all in one.
Okay, so we've established this massive geographical container, the region. Now let's drill down one more level of granularity. We're moving from the whole regional area, like a central 1, to specific zones within it, like a central 1A or B.
Right.
Why do we need this internal division? What exactly defines a zone?
A zone is an isolated physical location within a larger region. Think of it as a single, self-contained data center or maybe a small cluster of them. Every GCP region has multiple zones, typically 3 or more, and they're identified by those suffixes, A, B, F, and so on.
Okay, but if the region is supposed to be this huge fault domain boundary, why bother with smaller divisions inside it? Why can't I just deploy everything in a central 1 and just rely on its regional resilience?
Because the region protects you from external catastrophes. The zone protects you from internal common operational failures.
Ah.
That is the key distinction. The first characteristic of a zone is fault tolerance, which facilitates that internal resilience. Zones are isolated from each other, but within the regional perimeter.
And what does that internal isolation look like practically? I mean, the region separation is thousands of miles. How far apart are the zones?
Often they're separated by at least a few miles, sometimes more, depending on the area. And crucially, they're powered by different power distribution infrastructures. They have distinct isolated cooling systems.
So if one power feed fails.
Or if one zone has a catastrophic localized cooling system failure, which is a very common type of outage, it will not cause a cascading failure in the adjacent zones in that same region. This physical and logical separation within that regional boundary is the single biggest factor in achieving what we call high availability.
I see. So the region protects against the hurricane that takes out the whole city.
Right.
The zone protects against the localized fire or the transformer blowout that takes out a single build.
Precisely. If you only deploy your application to a central 1A and that zone experiences an issue, your application is down, period.
But if you spread it out.
If you deploy your application across A, B, M, O, F, you have immediately engineered in fault tolerance against a single data center failure.
And the mechanism that lets us spread our application across these separate physical buildings without a massive performance hit, that must be the second characteristic. Low latency, internal.
Absolutely. While regions are separated by, high latency public networks or long-haul private fibers, zones within the same region are connected by this ultra-high-speed, dedicated low-latency network fabric.
And that network is optimized for what kind of communication?
It's optimized to allow synchronous communication. This is vital because if you're running a clustered database, say a MySQL or a PostgreSQL cluster, the primary instance in Zone A needs to replicate its data to the replica in Zone B almost instantaneously to maintain consistency.
Right. If the latency between zones was high, that synchronous replication would just grind the whole application to a halt.
It would be unusable.
So the engineering challenge here is maximizing physical isolation for fault tolerance, while at the same time minimizing network latency for data consistency.
It's a really delicate balancing act. They maximize the physical distance to mitigate those localized disasters, but then they use dedicated dark fiber and specialized network hardware to negate the time penalty for that short distance. It's what makes multi-zonal deployment so efficient and really seamless for the application layer.
Before we move on, you mentioned a nuance about selection, resource availability. What does an architect need to know about the fact that not all resources are available in all zones?
Yeah, this one often catches new architects by surprise. While basic things like compute engine VMs are pretty much ubiquitous, specialized hardware is often rolled out incrementally or it's restricted because of infrastructure constraints.
So you're talking about things like cutting-edge GPUs or TPUs for machine learning.
It's exactly cutting-edge tensor processing units or extremely high-memory virtual machines, or specific network interface cards you might need for high-frequency trading. These are specialized, highly expensive, or physically large resources.
And why would Google restrict that to a specific zone? Is it just about supply?
It's about resource optimization and deployment logistics. It might be more efficient to install a limited supply of next-generation TPUs into only Zone B and Zone C of a region, rather than spreading them thin across all the available zones.
So what does that mean for me, the architect?
It means that if your specialized AI workload must run on that specific TPU type, your zone choice is dictated purely by inventory. It overrides that general principle of spreading resources for HA. You have to check the zone inventory for specialized resources before you commit.
That's a great operational detail to remember. So the takeaway here is clear. Zones are the unit of internal resilience and high availability. They're the workhorse for surviving the day-to-day failures of computing.
That's it exactly.
Okay, let's synthesize the relationship between these two layers. This is the moment where an architect's strategy is really defined. We need to clearly label what each layer is responsible for when it comes to application resilience.
This hierarchy really does define your operational goals. And we associate two key terms with these goals: high availability, or HA, and disaster recovery, DR.
So let's start at the zone level. Where does zone deployment fit?
Zones equal high availability. It's that simple. HA is all about minimizing downtime and ensuring service continuity against localized, common day-to-day failures.
So cooling, power, a localized network glitch, hardware failure?
All of that. By deploying an application across 3 zones within a single region, you achieve internal fault tolerance. If Zone A fails, the load balancer immediately redirects all the traffic to Zones B and C.
And the service stays available, the end users might not even notice it happened.
They might see a slight momentary delay, at worst. That's resilience measured in seconds. If Zone A is offline for 6 hours for maintenance or a repair, the application just doesn't care because B and C are still running.
So HA protects the application within its primary geographic footprint. Now, when we zoom out, we look at the region layer.
And that's where DR comes in. Regions equal disaster recovery and data residency.
Why is that distinction so important?
Because regions provide that geographic isolation we talked about. DR is the strategy for protecting against a catastrophic, widespread failure that wipes out an entire regional footprint.
The natural disaster, the massive utility failure, the unrecoverable event.
Exactly. To achieve true DR, you must deploy your redundant application instance and its replicated data to a separate, physically isolated region, often across oceans or continents.
Okay, but maintaining that redundant deployment across thousands of miles sounds incredibly complex, and I have to imagine very expensive. The data synchronization alone must be a massive financial and engineering burden.
It is the single biggest operational cost in DR, without a doubt. When you're setting up a multi-regional DR strategy, you have to grapple with 2 things: RPO and RTO.
Recovery point objective and recovery time objective.
Right. RPO is how much data loss you can tolerate, and RTO is how fast you can bring the application back online. Achieving a near-zero RPO across continents requires continuous, asynchronous, high-bandwidth data replication. That incurs significant network egress charges and computational overhead. DR is not cheap, it's an insurance policy.
And then there's the data residency aspect again, which complicates things.
It's often the non-negotiable side of DR. You might want to replicate your data from Europe to Asia for maximum geographic separation, but if EU laws require the data to stay in Europe, your DR strategy is immediately constrained.
So you have to replicate only to another compliant European region.
Exactly. You sacrifice that maximum geographic separation for regulatory necessity.
Let's ground this with our case of the global e-commerce company, using these HA and DR terms.
Okay. So if you look at their strategy, they're using multi-regional deployment for their website front end, say in the US, Europe, and Asia.
That's their DR strategy.
That's their DR strategy, exactly. It ensures global access and protects against an entire continent's infrastructure failing. It's also their latency optimization mechanism.
So the moment the East Coast US cloud fails, the DNS and the load balancer shift all that traffic to the European site.
Instantly. Then we have the regional data residency requirement. Their order processing systems that handle EU customer data are isolated strictly in, say, Europe West 1. This is a hard boundary driven by law.
And finally, the HA piece.
Right. And finally, within a central one, they use multi-zonal deployment for their front end, spreading it across 8 A, B, and IF. This is their high availability mechanism. It guarantees that local U.S. users can always transact, even if one data center in Iowa goes down for maintenance or a minor power interruption.
It paints such a clear picture. You use zones for internal short-term resilience, and you use regions for external catastrophic protection and regulatory adherence. The architect has to select both and understand the trade-offs in complexity and cost at each level.
And that practicality is immediate for anyone learning this. Like you said, when you go to set up a new instance, you have to specify both the region, the boundary for your DR and residency, and the zone, which is the boundary for your HA. You're explicitly forced to consider this tiered resilience model for every single resource you deploy.
We've covered the geographic footprint, the physical locations where services reside. Now we move up a layer to the management infrastructure. What about the services that seem to exist everywhere at once? And they're the same whether I'm deployed in Iowa or Belgium. I'm talking about the global services.
The global services are, I like to think of them as, the operational brain of the entire platform. They're the layer that abstracts away the physical geography, allowing you to manage this complex, distributed infrastructure from a central point.
So they're not tied to a specific region or zone?
By definition, no. So if regions and zones are the data plane, where the actual compute, storage, and customer data live, then global services are the control plane.
The control plane. They manage the configuration and policies of the whole ecosystem.
That is the essential distinction. They are control plane functions. They manage, configure, deploy, and enforce policies across all the regions and zones you use.
And that enables two key characteristics, right?
It does. First, they are globally available, accessible consistently from anywhere. And second, they often manage globally distributed data like access policies, domain name records, or routing rules that must be universally consistent and low latency no matter where the user is.
Okay, let's dive deep into the specific functions of let's call them the essential four global services, starting with the one we flagged early on as critical, Cloud IAM.
Cloud IAM, or Identity and Access Management, is maybe the most critical global service. It is the centralized mechanism that controls access to every single GCP resource.
Every single one.
Every single one, whether that resource is a global object like a DNS record or a zonal compute engine instance.
Yeah.
The policies are defined globally. You write the policy just once, but they are enforced consistently across the entire platform.
What's the consequence of that global nature? It sounds powerful.
It creates enormous efficiency, but also enormous risk.
Yeah.
Because the policy is global, if you grant a developer access to compute instances, that developer potentially gains access to all compute instances in all regions, unless that policy is explicitly scoped down.
I see.
So the challenge for the architect is leveraging that global simplicity of IAM while making sure that policies are refined using resource location as a critical variable.
So you're saying I use the global control plane to define the rule, but I use my local geographic knowledge, the region or the zone, to define the scope of that rule.
Exactly that. For instance, you might use IAM to grant general monitoring access globally, but you'd restrict access to the sensitive financial data in the Europe West 1 database cluster to only a specific user group, and you do that using a conditional IAM policy that's based on the resource's location label. The global system interprets and enforces that location-specific rule.
Okay, that makes sense. Moving to network routing integrity. Cloud DNS. How does its global nature guarantee high availability?
So Cloud DNS manages your domain name records. When a user requests your domain name, Cloud DNS resolves that request. And it's designed to be globally distributed using a technique called anycast.
Anycast.
Right. This means the same IP address is advertised from many different locations around the world. So when a user queries that IP, the network automatically routes them to the geographically closest DNS server.
And why is Anycast so important here?
Well, if one region, say, the primary point of presence for your DNS infrastructure suffers a massive failure, the user's request is just rerouted by the network fabric to the next closest healthy DNS server, which might be thousands of miles away.
But the records are replicated everywhere.
Because the records are globally replicated across all these servers, domain name resolution stays intact. It guarantees continuous accessibility. Without a global DNS, a regional outage could make your application unreachable, even if your servers in other regions are perfectly healthy.
That's resilience at the most fundamental naming level.
Right.
Let's talk about traffic distribution, cloud load balancing, the global version.
Yeah, global load balancing is the traffic cop of the control plane. It distributes incoming user traffic across your deployed services in multiple regions. It's absolutely crucial for maximizing both availability and performance.
And it also uses Anycast IPs, right?
It does. The global HTTPS load balancer also uses Anycast IPs, which means your users around the world connect to the nearest possible point of presence at the network edge.
And how does it intelligently route that traffic to, say, my deployment in Iowa versus my deployment in Belgium?
It continually runs these background health checks on all your backend services in all your regions. It maintains a global real-time map of the health and capacity of all your deployments.
So if a user in New York queries my site,
The load balancer routes them to the nearest healthy region, maybe US East 4, to minimize latency. If US East 4 then fails, the load balancer instantly detects that failure via the health checks and automatically routes all subsequent traffic to the next closest healthy region, maybe US Central 1.
so it's actively enforcing our architectural decisions about latency and disaster recovery in real time, all from a centralized global control plane.
Precisely. It turns your multi-regional deployment from just a series of independent sites into one cohesive, resilient service layer.
And finally, let's discuss security at the edge. Google Cloud Armor.
Right. Cloud Armor provides global protection against web application threats. It basically functions as a security firewall at the very edge of the Google network before traffic even gets to your regional application deployment.
And its global presence is key here.
It's absolutely key because it can filter out volumetric DDoS attacks, distributed denial of service at massive scale.
Why is it so vital that this is a global service and not a regional one?
Because DDoS attacks are globally launched events.
Oh.
You need a defense mechanism that can absorb incoming traffic measured in hundreds of gigabits or even terabits per second.
And a single region can't handle that.
No. By having Cloud Armor deployed across Google's entire global network edge, it can distribute the absorption and the filtering of that malicious traffic across its entire footprint, protecting all your regional assets at the same time.
And it does more than just DDoS.
Oh, yes. It also applies crucial web application firewall rules, WAF rules, to protect against common Layer 7 attacks like SQL injection or cross-site scripting, and it does it before the bad request ever reaches your regional server in Iowa.
That creates a unified security perimeter that sits ahead of all your localized infrastructure. It's a perfect example of global management simplifying regional complexity.
To summarize how they all integrate, the e-commerce company uses IAM to manage access uniformly across Iowa and Belgium. They rely on Cloud DNS for domain integrity. Global load balancing routes users to the nearest, fastest available deployment. And Cloud Armor defends against global internet threats that are targeting their regional deployments. This centralized control plane is what makes massive scale manageable.
This moves us directly to the architect's chair. We've defined the map, the isolation, the central control layer. Now, the listener has to make the decision. When picking a location, we establish there are 6 critical and often conflicting factors they have to weigh. This is where the true trade-offs happen.
It is. Selecting regions and zones is a real commitment. It impacts your costs for years, and it determines your compliance posture. Getting it wrong leads to some very expensive refactoring down the road.
So let's discuss these 6 factors as a structured decision matrix. Factor 1, latency. This is just driven by physics.
Yes. You must prioritize regions that are geographically close to the majority of your users. But the discussion needs to shift from just minimizing delay to understanding the cost of poor latency.
What do you mean by that?
Well, research consistently shows that every 100 milliseconds of added latency increases bounce rates and reduces conversions for commercial sites. The business impact of user frustration cannot be underestimated. If your primary market is Japan, deploying in Asia Northeast 1 in Tokyo is essential, even if compute costs there are a little bit higher than in the US.
So performance often acts as a non-negotiable floor, even if it adds cost.
Correct. Latency is the gateway to the user experience. If the experience is terrible, the most compliant, cheapest system in the world won't matter at all.
Factor 2, availability, HA. How do we ensure the design promotes high availability?
This is purely a zonal decision. Achieving HA means deploying across multiple zones within your chosen region. The architectural best practice is always multi-zonal deployment for mission-critical applications.
So at least 2, preferably 3.
Exactly. You have to ensure the service is deployed to at least 2, preferably 3 zones to ensure that internal fault tolerance. If you architecturally choose a single zone deployment, you are explicitly accepting the risk of downtime from very common infrastructure failures.
And the cost difference between deploying in 1 zone and 3 zones is minimal compared to the massive cost of downtime. This seems like a no-brainer investment.
It is the easiest resilience mechanism to implement, and it's the cheapest form of redundancy because there are no long-haul network costs involved.
Okay, factor 3, cost. How do architects navigate this variable pricing structure?
Well, pricing varies significantly between regions. It's based on local operational costs, things like land, power, local tax structures, and network infrastructure costs. For example, compute resources in historically established regions like Central 1, might be significantly less expensive than in newly deployed smaller regions in, say, Latin America or Africa.
Where utility costs or local market dynamics drive prices up.
Right. So an architect has to actively engage in financial modeling. The real opportunity to optimize cost involves tiering your infrastructure.
How does that work?
For your latency-sensitive front ends, you pay the premium to be close to the user. But for non-latency-sensitive workloads, things like nightly batch jobs, data archiving, historical processing, you can choose the absolute cheapest region available globally, regardless of user location, to minimize your infrastructure spend. The smart architect separates high-value, latency-sensitive services from bulk processing services and optimizes the regions accordingly.
Factor 4. Data residency and compliance. This is the ultimate veto.
This is the factor that overrides all others. If a regulation like GDPR or IPI or some financial regulatory mandate dictates that data must remain within a specific legal jurisdiction, the architect's choice is narrowed immediately to the single region or set of regions that meet that requirement.
It's not optional.
Not at all. If the law says your data must be processed within the borders of Germany, your cost and latency preferences are irrelevant. You choose the German region.
This means an architect needs to be a hybrid expert, part engineer, part legal scholar.
They need to understand the regulatory landscape of their target market, or they risk massive fines and legal penalties. Compliance establishes the mandatory outer boundary of your deployment map.
Factor 5, service availability. We talked about this at the zonal level, but what about regionally?
An architect has to ensure that the specific technology stack they need is actually deployed in the target region. Older or smaller regions might not offer the latest specialized machine types or specific new platform services.
Like a new flavor of Cloud Spanner or advanced network features.
Exactly. If your application requires a specific version of a cutting-edge service, you must verify that the target region supports it, even if that means compromising slightly on cost or proximity to users. You can't build a product on components that just aren't there.
So you have to check the release notes and the regional availability tables before you even start development.
Absolutely. The decision shifts from where should I put this to where can I put this, given the technological constraints.
And finally, factor 6, disaster recovery, DR.
As we've established, DR is achieved by deploying resources in multiple regions. This provides protection against the largest scale failure events. The architectural challenge here is defining your RTO and your RPO and designing the necessary data synchronization and failover mechanisms.
And the more stringent your requirements for, say, RPO.
The less data loss you can tolerate, the higher the cost and complexity of the cross-region network fabric and synchronization systems you'll need to implement. DR is the final layer of resilience, and it carries the heaviest price tag in terms of ongoing operational expense.
That six-factor framework provides a really clear path for evaluation. So to summarize the best practices, deploy across multiple zones for resilience, that's your HA. Use global load balancing to efficiently distribute traffic. Choose regions close to users for latency.
Right.
Actively research and use cost differentials to optimize non-critical workloads. Strictly comply with residency mandates, that's the veto power. And finally, invest in multi-region deployment and regular testing for true disaster recovery.
And that last part is key. A plan that hasn't been tested across regions is just a theory. You have to validate that the failover route works and that your data replication is actually fast enough to meet your RPO goals when you're under duress.
Let's cement all this knowledge by applying this comprehensive six-factor framework to a high-stakes, real-world example: the global trading platform of a financial services company. This industry faces extreme pressure on speed, security, and compliance.
Yeah, this scenario forces an architect to balance all 6 factors at the same time. The challenge is crystal clear. Provide ultra-low latency access to traders all over the world and adhere to incredibly strict regulatory requirements concerning data residency and system security.
So walk us through their strategy, starting with geography and speed.
Okay, so the multi-regional strategy. To minimize latency for traders in major financial hubs and to ensure DR, they deploy in diverse regions, maybe East 4 in Northern Virginia, which is often closest to the financial exchanges, Europe West 3 in Frankfurt, Germany, and Asia Southeast 1 in Singapore. This spread ensures that traders in New York, London, and Tokyo all benefit from minimal network travel time.
So that's directly addressing factor 1, latency, and factor 6, DR.
Exactly. If the entire U.S. East Coast grid fails, the global platform stays operational via Europe and Asia.
And within those critical regions, how do they handle the high availability required for trade execution? You can't have downtime there.
No, you can't. So, the multi-zonal strategy. Within each of those chosen regions, all the core platform components, the trading engines, the order matching systems, the market data feeds, are deployed across at least 3 zones. This is paramount for Factor 2 HA. They cannot tolerate even a minute of downtime from a localized failure.
So if a cooling system fails in one zone in Singapore,
the trading platform immediately fails over to the other zones in Singapore without disrupting the trading flow at all.
And they must rely heavily on that global control plane to manage all this complexity.
Absolutely. They're relying on Cloud IAM to manage access permissions uniformly, ensuring only authorized, authenticated traders and analysts can place orders, regardless of which regional instance they connect to.
Universal security.
Right. They use Cloud DNS to ensure their primary trading domain name is always resolvable globally, avoiding single points of network failure. Global load balancing handles the distribution, directing traders to the fastest available region based on their physical location, while ensuring immediate failover if a region becomes unhealthy.
And Cloud Armor.
And Google Cloud Armor, it's essential. It provides that centralized protection against malicious market manipulation attempts or targeted DDoS attacks aimed at destabilizing the trading platform.
Now let's address the cornerstone requirement, data residency, factor 4.
This is critical. Well, the front-end trading engines are multi-regional, sensitive client records, transaction histories, and specific regulatory reporting data must reside and be processed only in regions that comply with the relevant laws.
So, for instance, data subject to EU regulations.
Right. Data subject to something like MiFID II, regulations in the EU must often stay within the European regions, like Europe West 3. This means their core sensitive database infrastructure is geographically restricted, even if the application logic that accesses it is globally distributed.
That's a great concluding thought on the case study. This multi-regional, multi-zonal approach, orchestrated by these powerful global services, it really is the ultimate blueprint. It ensures the platform is highly available, scalable, secure, and compliant, successfully navigating that tension between performance, resilience, and regulatory boundaries.
The complexity of the architecture is directly proportional to the criticality of the data and the demands of the business. You use zones for internal speed and resilience, regions for external protection and legal adherence, and global services for unified, scalable management.
This knowledge is foundational for designing any truly scalable and cost-effective cloud environment. You really do need to know your map before you start building.
Indeed. And knowing where your resources sit is the precursor to understanding who's allowed to touch them. The location itself becomes a security attribute.
Which brings us right back to our theme. Global control over local resources. We've established that resource location is key to defining access policies via Cloud IAM. So here's a provocative thought for you to chew on until our next deep dive.
Okay.
IAM provides one centralized control plane for the whole world. If resource location is key to defining access policies, how does the global nature of Cloud IAM change your approach to security, knowing that one global policy misconfiguration could instantly affect data access in Iowa, trading systems in Belgium, and user profiles in Taiwan simultaneously? Think about the power and the danger inherent in that single point of global security control.